everyone. I am Vineet Kumar Sinha from ABS Engineering College, Kazipur. In this video lecture series, we have been discussing the subject materials engineering. And in the unit 1, that is crystal structure, today the topic which we are going to discuss is hardness, Rockwell, Brinell, and Vickers. So let us start. As per the syllabus coverage, in this video, we'll discuss hardness at length. That is, what are Rockwell hardness testing, Brinell hardness testing, Vickers hardness testing, and also their relation to strength as per the syllabus. So, first of all, let us see what is hardness actually. So, hardness is a measure of material's resistance to localized plastic deformation. How much the body or the material resists to the localized plastic deformation caused by any scratching or indentation, basically in the form of compressive load. So it measures the resistance of a sample to material deformation due to a constant compressive load, compression load from a sharp object, so that a scratching or indentation can be achieved. They are classified under mechanical characterization of material. Not necessarily it is the mechanical property, but it comes under or classified under mechanical characterization of material. Because as per the testing techniques or the testing method, the number, your value gets varied. A hardness test is typically performed by pressing a specifically dimensioned and loaded object. That is called indenter. Indenter through which the load compressive load is applied by pressing is a specifically dimension whose dimension is fixed, and the load applied on it is also fixed as per the scale or different methods of hardness testing. Indenter into the surface of the material which has been tested. The hardness is measured by measuring the depth of indenter penetration after applying certain measured load or specifically mentioned load and specifically loaded object and dimension indenter, how much depth is created, or the penetration, how much penetration is there, how much depth of penetration is there, or by measuring the size of the impression left by the indenter. There are two methods of getting the hardness result: by measuring either the depth of indenter penetration or by measuring the size of the impression left by the indenter. Now, few more salient features. Indenter may be rounded or pointed. It may happen, it may be rounded or pointed, made from very hard materials so that the penetration can be made, such as hardened steel which has already been hardened, tungsten carbide, which is also very hard, and diamond, the hardest element known till date. So hardness number, what we obtain from various testing techniques, testing methods, in terms of hardness number, is determined by the difference in depth of penetration, how much depth of penetration is there in a particular scenario, situation, resulting from the application of an initial minor load followed by a larger major load. Two types of load is applied one by one consecutively. With initial, it is penetrated first by initial minor load and then followed by a larger major load. This is done to utilize the utilization of a minor load enhances the test accuracy. The result is being compared for the minor load. When minor load was applied, what was the depth of penetration? And then when larger major load applied, then this was the penetration. So that minus penetration when larger load applied minus the initial load applied will get the true value, or the test accuracy gets enhanced. Hardness tests that measure the depth of indenter penetration include the method through by measuring the depth of indenter penetration is the testing methods include Rockwell, instrumented indentation testing, and also ball indentation hardness. But basically, the hardness tests that measure the size of the impression left after indentation, what is the size and what is the diameter of that impression left by the indenter, That methods include Rockwell testing, Vickers hardness testing, Noob's hardness testing, and also Brinell hardness testing. So let us see briefly one by one. In Vickers test, very small diamond indenter. The indenter here is diamond indenter in Vickers test having pyramidal geometry, specified dimension indenter. So the geometry is pyramidal in Vickers test, and the indenter's material is diamond, is forced into the surface of the specimen to be measured. The surface of the specimen for which the hardness test is being done, or to the hardness number is to be measured. In Vickers test, the indenter applied is diamond, made of material diamond, having pyramidal geometry. The resulting impression is observed under a microscope and measured. This measurement is then converted into a hardness number through relation hardness Vickers equals to 1.854 F upon D square. Through this relation, Vickers hardness number can be obtained. There is a method of writing with hardness values. HV stands for hardness Vickers, or is pronounced as hardness on Vickers scale. So hardness on Vickers scale is equals to 1.854 into F. F here is the force applied in kgf upon d square. D square is diameter of the indentation. This is the situation, and this is the picture where we can understand that this indenter, the diamond indenter, is having, this is the specimen is having a tip of diamond having this pyramidal shape and having 136 degree centigrade, 136 degree angle in between the two surfaces. The square base pyramidal indenter is there, and the impression left is measured after the impression is made. It is, if it is D, small d represented by small d, this is sample and this is impression. So after measuring D1 and D2 and having average of that is make D, the value of D. So HV can be calculated with this relation. HV equals to 1.854 into F upon D square. Coming on to Brinell test, Brinell hardness test. Here a hard spherical indenter, not pyramidal, spherical indenter is forced into the surface of the sample to be tested. Here the indenter's geometry is spherical rather than pyramidal. And it is also hard material, otherwise the penetration would not have been achieved. The Brinell hardness number is a function of both the magnitude of the load. It is the formula for calculating is taking into account, or it is having the function of both the magnitude of the load and the diameter of the resulting indentation. So size of the indentation also, and the magnitude of the load, how much load is being applied. This diameter is measured with a special low power microscope, especially designed for measuring this Brinell test, Brinell indentation. From the measured diameter, the BHN or Brinell hardness number is being calculated by formula BHN, Brinell hardness number, equals to F upon is equal to F upon pi by 2D into D minus root over D square minus DI square, where capital D is the diameter of the indenter, spherical indenter, which is being used in Brinell test. The capital D is the diameter of the indenter diameter. F is applied force in kgf, applied force in kgf, and DI is the diameter of indentation, indentation diameter DI. So Brinell hardness number can be calculated. This can be solved Since it is a spherical, we can solve this equation, this triangle, and have a formula or have the relation can be deduced like BHN equals to F upon pi by 2 d into d minus root over d square minus di square. So Brinell hardness number or Brinell hardness can be achieved from this relation after having a indentar of spherical shape and hard tungsten carbide or hardened steel can be used for Brinell hardness test. Similarly, for Rockwell hardness, the indenter is having an included angle of 120 degree. It's a cone in the shape of cone, and also the indentation after measuring the size of indentation, we can have the Rockwell hardness achieved. To have a comparison of hardness testing techniques, various hardness testing techniques can be tabulated as follows. If for a test as Brinell, the indenter is 10 millimeters spare of steel or tungsten carbide. Shape of indentation is spherical, having the capital D diameter of the spherical indenter and small d is diameter of the indentation, or D or Di as we were seeing in the last slide. The top view will have a small diameter D. Load would be symbol as P. Formula for hardness number HB hardness Brinell. HB means hardness Brinell equals to 2P upon 5D into D minus root over D square minus D square. The same relation as we have seen earlier. For Vickers micro hardness, Vickers testing techniques generally used for micro hardness. Here the diamond indenter was there and pyramidal shape was there. We have already seen, and this having an included angle of 136 degree. D1 and D2 would be the measurement we have to make for the indentation. P would be the load. Then HV hardness Vickers, hardness and Vickers scale. Hardness on Brinell scale, hardness on Vickers scale equals to 1.854 P upon Di square that we have already seen in the previous slide. Similarly, there is a hardness testing technique called new micro hardness testing technique. Here also the indentation is diamond and diamond material and having a shape of pyramid, and we can calculate this Noob's hardness on Noob scale equals to 14.2 into P upon L square, where these are the dimensions. Rockwell and superficial Rockwell, for this, various scales are there, A, B, C, D, with having a different set of cone-shaped indenters, having 1 by 16, 1 by 8, 1 by 4, 1 by 2 inches diameter steel spares, having an included angle of 120 degree because it's a cone, and 60 load applied would either be 60 kg, 100 kg or 150 kg depending, and similarly the nomenclature of the scale would be obtained. Superficial Rockwell is having 15 kg, 30 kg and 45 kg load applied for micro hardness testing. So this is the comparative table for various hardness testing techniques. Also, if we can see Rockwell scales, what are the various Rockwell scales? So these are the regular Rockwell scales where scale symbols would be Rockwell scale A or B or C or D, E, F, G, H, K, L, M, P, R, S, V. These are the various scales. Here we can see indenter type are either a sphero-conical diamond or ball having 1.5, 1 by 16 inches, then diamond, sphero-conical diamond, or ball having 1 by 8 inches, 1 by 16 inches, 1 by 16 inches, with various load in kgf. The initial load or minor load would be 10 kgf only for all the scales, and my major load would be either 60, 100, or 150 kgf. The typical applications are also mentioned for which you can have a look and have a grip of the things. Coming on to Rockwell hardness scale that we have seen in the last slide. Here also it can be tabulated as A, B, C, D, E, F, G, H, K scale symbols. Indenter having maybe diamond or 1 by 60 inches ball, spherical ball, or 1 by 8, 1 by 16, 1 by 8, 1 by 16. These are the values of the indenter ball. Having major load, variation in major load would either be 60, 100, 150, 100, 100. In terms of either it is 60, either it may have maybe 60 or 100 or 150. Only three categories are there. Minor load are all 10 kgs, and depending on the diameter size, combination of diameter size and major load, we can have various scale symbols like A, B, C, D and various. So every after measurement, after making the value of putting the value of certain material of having hardness on Rockwell hardness testing, we have to always mention the on which scale on Rockwell hardness A, B, C, or D, or which scale we have always it is to be mentioned. So just mentioning the Rockwell scale, it is clarified that what is the indenter, what is the size of the indenter, and also what is the major load category applied on for that indentation. Superficial Rockwell hardness scale, for superficial measurement or small measurements, scale symbol would be in place of ABC, it would be 15 and 30 and 45 and 15T, 30T, 45T, W. As per whether it is diamond indenter, 1 by 16 inches ball indenter or 1 by 8 inches ball indenter with major load 15, 30, 45, 15, 30, 45, 15, 30, 45. So if the indenter is 1 by 16 inches ball and the major load applied is 15 kg, then that scale would be called 15T. Similarly, if 1 by 8 inches ball would be used as indenter and 100 kg major load would be applied after the application of 10 kg of minor load, then Rockwell scales E, it will be considered as Rockwell scale E. The measurement is on Rockwell scale E. So what is the significance of all these scales, or how do we measure on that scale? For each Rockwell scale, hardnesses may range up to 130. The value may come up to 130. However, as hardness value rise above 100 or drop below 20 on any scale, they become inaccurate. The accuracy level becomes low after the value is coming for if you are measuring certain material indentation as per certain Rockwell scale A, B, C, and as per the scale, if you put the indenter and the load apply on it, the load and the value, if the value is coming more than 100 or less than 20, then the value would be slightly inaccurate. The calculation would be inaccurate. So because the scales have some overlap, in such a situation, it's best to utilize the next harder or softer scale. So if you are using, if Rockwell on Rockwell B, it is coming 120 value, then we may upgrade it to Rockwell C, then it will come to maybe 40, 50, and the value would be more accurate. Inaccuracies also result if the test specimen is too thin. There are few criteria which should be met so that the result or the hardness value is uh, accurate or within uh, good parameters. So inaccuracies also result if the test specimen is too thin, if an indentation is made too near a specimen edge, or if two indentations are made too close to one another. So the accuracy will not be proper if the test specimen on which the penetration is being done is too thin and it is too near a specimen edge, there nearby a edge of the specimen is there, or it is made too close to one another. Suppose one indentation is made at a place and the second indentation, the second reading will be taken simultaneously side by side with very close to each one another. Then also the result would be not that much accurate. So it should be avoided. Similarly, specimen thickness should be at least 10 times the indentation depth. And what are the other criteria? The thickness of the specimen, it is not be too thin. So how much it should be? It should be at least 10 times the indentation depth. What is being indented? How much load we have? Suppose we have put in 100 kg of load, then the indentation size or the diameter, it should be such that it may be the total thickness of the specimen would be at least 10 times of the indentation depth. Allowance should be made for at least 3 indentation diameters. So there the two between two consecutive readings, there should be at least 3 indentation diameter gap should be there between the center of one indentation and the specimen edge or the center of a second indentation. From every center of indentation, the specimen edge or the center of the second indentation should be at least 3 indentation diameter apart. Furthermore, testing of specimens stacked one on top of another is not recommended. Also, accuracy is dependent on the indentation being made into a smooth, flat surface. So first we have to make the surface flat enough, and also not stacked one on top of another, and having at least 3 indentation diameters apart from the edge or the second center of another indentation, and 10 times the indentation, at least 10 times the indentation depth is there. Then the reading would be more proper and more accurate as per the. And also, if the value is coming more than 100, you have to upgrade to the next scale, or the value is below 20, we should be scaled down to one lesser scale. These are the things that needs to be considered while measuring the hardness through Rockwell testing. This is a general comparison of several hardness scales. So the far left is noob hardness, 100, 200, 300, 400, 600, 800, 1000. These are the values which can be obtained through noob hardness test. Brinell hardness, we can have an overlap of 5, 10, 20, 50, 100, 200 till 10,000 value can be obtained of Brinell hardness. So a 600, we can see that 600 noob hardness value is corresponds to 500 Brinell hardness value. Similarly, on Rockwell B scale, it is more than 110 also, maybe 120, 130. And on Rockwell C, it would come 50, 45 or 50 only. So we can see if a value of a material on the Rockwell B scale is 120, it should be measured on Rockwell C also for better accuracy, what we have discussed earlier. To get a value around 50, and that would be more accurate. As soon as it gets above 100 or above 110 or above 120 and below 20, it should be moved to next scale or previous scale. And this is the far right is the most hardness scale, which were earlier before this hardness testing techniques were developed. These were the most hardness number or hardness scale was applicable to identify the hardness values of various materials. So that one was the value of talc, and 10 was the value of diamond, which was the hardness material known. In between, corundum or sapphire was 9, topaz was 8, quartz 7, and apatite was 5, and so on. Calcite, gypsum was 2. So we can refer as a value of 7 quartz on the Mohs hardness is coming as 60 for Rockwell C, and around 700 for Brinell hardness, and around 900 for Noob's hardness. The various materials and where it lies on the hardness of scales are mentioned here, that nitrided steels are around 1000 Brinell hardness number, cutting tools around 700 to 800 hardness number, Brinell hardness number. Similarly, most plastics are very not that much hard and is having only 15 to 20 Brinell hardness number, and very less between 1 and 2 of the most hardness scale. So this is the rough comparison of various hardness scales, and if any material is having 500 Brinell hardness number, then it is only having 50 or 55 Rockwell C hardness scale value. So like this, if we are mentioning hardness number or hardness, we have measured hardness on certain scale, we have to mention on which scale that reading is mentioned. So always we have to write HB something, hardness on Vickers, or hardness Brinell, or hardness Noob. We have to mention the hardness scale, or hardness Rockwell C, HRC, or HRB, hardness Rockwell B, and then that value to properly mention the hardness value of the material. Now coming on to the last segment, that is correlation between hardness and tensile strength. The relation of these hardness value with tensile strength. How it is, whether it is related or how is it related, that is of significance, because tensile test strength can be measured only through tensile test. What we have discussed in the lecture, one or two lecture back, when we were discussing the tensile test or compression test, that we have to take on that universal testing machine and the stress strain curve we need to plot, and a lot of effort would be required. So if there exists any correlation between hardness and tensile strength, then hardness can be measured very easily on any suitable scale, and it is a localized plastic deformation, so it can be easily done, and comparatively easier is the measurement of hardness value. So if there is a relation between hardness and tensile strength, then if we measure hardness, we can randomly guess the tensile strength of that material. So both tensile and strength and hardness are indicator of a metal's resistance to plastic deformation. Both are the indicator of the resistance to plastic deformation. Consequently, they are roughly proportional. As shown in figure, if we see that this figure, then Brinell hardness number is on this scale, on this x-axis, tensile strength is on y-axis, and how it behaves, and uh, this is the tensile strength in psi, and various steels, cast iron or brasses in red, blue and green, it is mentioned here in figure. And also the HRB, Rockwell hardness B scale, is plotted over here. So the same proportionality relationship does not hold for all metals. As a thumb rule, for most steels, the hardness Brinell, HB, and the tensile strengths are closely related. So Brinell hardness scale, the value on the Brinell hardness scale, and tensile strength. This is the tensile strength value, and here in terms of MPa and here in terms of PSI, 10 power 3 PSI are related according to the formula. Tensile strength MPa is equals to 3.45 into HB, and also in terms of PSI it is equals to 500 into HB. So if we know the HB value, or if in Brinell hardness test is very simple, as we have seen, the spherical indenter were used and 10 spherical indenter, and the material was either tungsten carbide or steel, hardened steel. So easily it can be achieved. The readings are taken on the localized surface or the flat surface, and if HB we know, if we get to know the HB after multiplying it by 3.45, we get the tensile strength of that material, roughly tensile strength of that material in megapascal. So it is easier to calculate tensile strength value or estimate tensile strength value for any material by applying Brinell hardness test or by applying a hardness value. If certain other test also we have done on certain other scales, the hardness test, then we can, through last slide where we compare the various scales of hardness, here this scale, we can estimate the value of Brinell hardness, and then after multiplying by 3.45, we can have an estimate of tensile strength in megapascal and also in PSI. So this is the correlation between hardness and tensile strength. So that was all about hardness, and with this lecture, the unit 1, which was crystal structure and also the mechanical properties and their measurement, the entire topics have been covered in the last 4-5 lectures. So in the next lecture, in the next video, we'll start unit 2, and subsequently other units will also be covered in the latter videos. Thank you.